Hi there, Tony Verbsky here. We're going to go over 6C today. I cannot tell you how much I like this chapter, even though it's the opposite of what I study. I'm an applied mathematician, mostly calculus stuff, and there's this other realm called statistics, which is what we're working on now. We are just touching the surface. This section I'm talking about today, this takes all semester almost in a regular statistics class, and we're going to do it in one lecture, so we are definitely just touching the surface. So what it comes down to is the normal distribution of data. Distribution. And you maybe have seen it before, and technically you don't really need this line here, but it's a bell-shaped curve of data. And then when you think of this, you think of a histogram, and your data is piled up nice with all these bars, you know, however you're looking at it. And then instead of looking at it like data stacked up and looking at the bars, we take a smooth curve when we run it through, let's say, the top of the bars or the top of the histogram rectangle. And when our data is bell-shaped curved, it's like maybe the SAT. Data, you know, a whole bunch of low scores, a whole bunch of tons of medium scores, and a few high scores. If you would like a grade distribution in class, you would like, here's the F's, here's the D's, here's the C's, here's the B's, and here's the A's. This is not normal. If you're a student, and especially a college level class, you don't want a normal distribution of data. But, and actually, to be honest, neither does a teacher. We don't want to be giving a whole bunch of D's and F's out. But if it were normal, we'd give the same amount of F's as A's, the same amount of D's as B's, and then we'd have predominantly C's for our class. Now, in the real world, there's these normal distribution. Let's say SAT score. Maybe the mean on math. Oops, I almost used the wrong letter. The mean X bar. Let's say it's 600 out of 800. And then maybe there's some type of other thing going on, like times to complete a certain task. Maybe it's 153 seconds. And it's normal. So kind of looks normal. And then we have this totally other situation that kind of looks normal, and etc. We got all these situations. So x equals 42, that'd be x bar equals, and hey, they also have a standard deviation, standard deviation, standard deviation, standard deviation. Now what we're going to do, instead of having one problem, two problem, three problem, we're going to work these all into a standard normal distribution. So you're going to turn this problem into, warp it in another realm and work on it over here. This one and this one. What we're going to do is devise a common method to solve hundreds of problems. So instead of having hundreds of problems, you only really need to learn how to work one problem in the standard normal distribution realm. Now, as said earlier, this takes all semester to understand, and sometimes you don't even get it in a semester. But the people who came up with this idea, they're really smart. Why would you have 100 different problems when you can have one? It feels like they almost made all this stuff up, but guess what? It actually works. No, so that's one phase of our lecture for today, and that'll be the second part. You guys kind of got it good. There's only really two things we're going to be doing here, and you just got to try to take the leap of faith and say, yeah, I believe you. I believe that's all going to work. And then I give you like 2 procedures, and then you get out of the section and you're good to go. But bottom line, if you really want to learn some useful mathematics, well, can't talk this morning, useful mathematics, take a class in statistics. As I said, it's not my field. I use statistics, and I used to abuse statistics, but now after teaching it for many a year, I have respect for the subject now. So, this is the part I had a hard time with, warping all problems into one. Anyway, let's get to the nitty-gritty of the section. So, if you have a normal distribution of data, and you find the mean, and if it's normal, the mean will be at the top of the peak. This doesn't whoop up like this anyway, it goes like this. I know you guys, those of you who are into my lectures, I think you find sometimes when I do dumb things like that, it's kind of humorous. Now, we're going to find a standard deviation, and the book says SD. So you go x bar minus SD and x bar plus standard deviation. And if it's normal, they're going to guarantee that 68% of data lies in the interval x bar minus SD, x bar plus SD. Now, this was a combination of calculus and statistics. They came together to prove this, but you just remember 68. Then 95% of the data lies between x bar minus 2 standard deviations and x bar plus 2 standard deviations. And then you just have to remember 95% lies in that interval. Now, the book didn't really talk about it, but they keep talking about what outliers might be. It turns out one definition of an outlier is anything outside this interval, the 95% interval, or 2 standard deviations out beyond the mean are going to be called outliers. But we don't really get to explore that. And finally, this zone here, right here, is x bar minus 3 standard deviations and x bar plus 3 standard deviations is the 99.7% of all data lies in that interval, which is, wow, that's a lot of data. Now, don't worry about it. Just trust me. 1 standard deviation away, 68%. 2, 95. 3, 99.7. So, this is kind of, it'd be really nice to have a great example here. So, what do you say we try to construct one that's acceptable? The book doesn't do it, but I got to do it. So, let's look at some data. Let's have number 1. Let's have 2 number 2s. Let's have 3 number 3s. Let's have 6 number 4s. Let's have 5 5s.